All right, I'm going to talk a little bit about the ways that we can measure distance, time, and hence speed and velocity in our laboratory, and you guys will be using a few of these things coming up, okay? First thing I referred to quite a bit is a speedometer, okay? And that's the thing that's in your car, of course, and on your bike computer, and so forth. Remember that speedometers generally don't tell you your average speed. They don't tell you your velocity. They don't tell you what direction you're moving. They just tell you your instantaneous speed, okay? And remember, they don't tell you about your average speed either, although some bike computers and some digital speedometers in cars can compute your average speed for a certain trip. But generally, a speedometer cannot do that for you, okay? Even more low-tech is a stopwatch and a ruler situation. You guys have used these, right? So if you want to measure how fast something's going, you just use a ruler or a meter stick. That's your distance. You time it with your stopwatch, your time, and plus or minus your reaction time, and so forth, okay? One of the things that I don't think I've shown you is called a ticker tape machine. These are super cool, okay? And what they are is they consist of this strip of paper that goes through this machine that makes a dot on the paper at equal time intervals, okay? So you can adjust it, say, it can make a dot, say, every second. So if something is going fast, for example, the dots would be more farther spaced out, okay, than they would be if this thing is going more slowly. Remember that the distance, the delta t between dots, would be kept consistent. And the other thing you can do is you can see whether something is speeding up or slowing down. The dots might start far apart and then they get closer together and so forth. So these are pretty cool, and you're required to be able to interpret ticker tape machine dots and just have an idea of kind of how they work. We'll do lots of examples of these things, okay? A couple other things that are really cool: motion detectors. We're going to use these quite a bit in the lab. Okay, what a motion detector does is it sends out a signal that reflects off of something, and then it comes back to the receiver, and then it can actually measure the distance and hence the speed. It makes a speed time graph for us. It's very, very, very cool. Okay, and we're also going to use photo gates, and we actually have a kinematics track that we'll use. Photo gates are cool. These are basically two laser beams that are set up, and it measures the amount of time that the laser is blocked. So, for example, this card, for example, would enter as soon as this edge enters that laser beam, it'll block it, and then when it leaves it will become unblocked, and so the computer can tell us with very, very, very high precision the amount of time that card stayed in that laser beam, and then of course we can measure the length of the card to have the distance, and that would give us distance over time would be the speed of that object, okay? So really, really cool stuff, okay? Here's an example of what I'm talking about with the ticker tape logic, okay? Go ahead and pause the video and read this example and give it a try. Okay, so this is like the intersection of a couple of roads, okay? And these are oil spots left on a road by a motorbike with a leaky filter as the bike travels from A to G. So I just want you to qualitatively describe the journey, okay? And what I came up with is this, okay? Generally, the farther apart the drips are, the faster the bike is going, okay? Closer together means the bike is going slower. And if you think about it, if it's standing still, there's going to be a huge, big, messy puddle, and they're going to be all over each other. Therefore, the bike is going pretty fast out here. It slows down as it approaches the intersection here. Okay, its slowest point looks like it's when it's making this right-hand turn around corner C. Okay, then it speeds up slightly and then kind of slows down again here, speeds up here, and then for some reason slows down slightly at point F. Okay, so just remember the leaky bike, the leaky oil. Let's say it's if we had a scale and if we knew that each dot was say 1 second apart, we could actually do some real physics and figure out what's going on with this bike. That would be pretty cool. Okay. Okay, the next example, go ahead and read this one and try this one on your own. Okay, the world land speed record was set in 1997 in a car powered by 2 engines. It's probably broken. It's probably even faster than this by now. But anyway, the aim was to exceed the speed of sound, which is about 343 meters per second in a normal temperature. To establish this record, the driver has to make 2 runs for the course. From the diagram, determine the average velocities for both trips. Okay, so pretty straightforward. The first part, I got positive 339.5 meters per second. And for the second part, I got negative 342.7. Okay, so you can verify those numbers. The driver did not exceed the speed of sound because he didn't break 343 meters per second as the speed on either trip. And the average of these two would be 341.1, okay? And what direction was the wind probably blowing? Well, probably from right to left in the diagram. Well, how do you know? Well, because it took less time to go from right to left than it did to go from left to right, okay? Kind of interesting. Okay, let's see, example 5. Go ahead and pause the video and try this one, okay? Here's your speed of light. Calculate the distance traveled by the light in one complete Earth year, and that unit of distance is called a light year. So a light year is not a unit of time, but it's a unit of distance, okay? So I'm using actually the 5-step problem-solving method to solve this one, okay? Which you remember from last year. Okay, so really what this amounts to is I have to convert years to seconds, okay? And then I use V equals D over T. Remember I said don't ever use D, so I'm changing that to S. Okay, all right, S equals VT, and I get 9.46 times 10 to the 12 kilometers. Man, that is a really long distance, okay? That is 1 light year, okay? All right, the time taken for light to travel from the sun to the Earth is an equally easy question. Okay, I'm changing my D to S. We don't use D anymore for displacement or distance. We use S. And I got about 8.3 minutes. This is pretty cool. It means that if the sun were to blow up or to stop burning all of a sudden, we wouldn't know about it for between 8 and 9 minutes. Man, pretty cool. Okay, here's another example. Try example 6. Pause it. Okay, car starts out from O in a straight line and moves the distance of 20 kilometers towards the right and returns to its starting position 1 hour later. Okay, the average speed would be its total distance over its total time. Total distance is 40 kilometers in 1 hour, okay? So that's 40 kilometers per hour, but its average velocity is 0 because its displacement is 0. It ends up exactly where it started, okay? Now, if the car starts out at a point 100 kilometers to the right and does the same thing, what's the average speed and average velocity? It's exactly the same. It doesn't matter where you start. If you start and stop at the same point, it doesn't matter if you're at 0 or O or wherever else or 100 kilometers away. Your displacement is 0, and therefore your velocity would be 0. Okay. Another example. Try this one. Okay. A little more complicated. Okay. So I've drawn this on a number line for you. Okay, so the initial displacement of a body moving with a constant velocity of plus 5 meters per second is negative 10, starts off at negative 10. And the question is, when does the body reach the point with the displacement 10 meters? How long does it take to get all the way over here? And what distance does the body cover in that time? Okay, well, it's really not a very complicated question. Okay, I'm thinking 5-step process again. So here's my distance, 20 meters, velocity is 5, t. I get 4 seconds, and obviously the distance covered is 20 meters. It's a very simple application of the ideas we've been talking about. It's going to get more complicated, like with this one. Try this one. Really pause the video and really try to do this one before you look at my solution. Okay, there are 2 bicycles. The bicycle A starts with initial displacement 0. So it's at the origin. It moves with a velocity positive 3 meters per second. Okay. At the same time, way out at 200 meters, cyclist B goes back towards the origin, moving at negative 2 meters per second. When do they meet, and where are they when this happens? It's very interesting. Okay, so I'll put this on a number line again. Okay, here's bicycle A starting at 0, going at 3 meters per second in that direction. Here's cyclist B starting way out here at 200, going in the opposite direction. Okay, now I'm using these equations that I came up with last time. Okay, so I have that the distance A equals its initial, the displacement A equals distance at 0 plus VA plus T, okay? So that comes from my V equals S minus S naught over T, okay? And I get that as being distance A is 3T and distance B as this equation 200 minus 2T. So what I have is I have 2 equations with 2 unknowns, okay? So it should be pretty easy to solve this. So when they meet, it's even easier than that. the distance A equals the distance B, okay? And then I solve for t, and I got 40 seconds, okay? And their common displacement would be 120 meters, okay? So you might notice that I'm actually using these terms, I'm actually using displacement and distance a little bit loosely here, so I'm going to be a little more rigorous about it. These really should all be vectors. These are displacement vectors, and these are velocity vectors, okay? So I just want to clear that up because I have been going back and forth between distance and displacement, okay? So the common displacement is 120 meters. So they meet like right in here somewhere, okay? Now another way to look at this, and we're going to spend a lot of time graphing kinematics, is if you think of this graphically, this is really cool, okay? So I made, I've made motion graphs for bicycle A and bicycle B, okay? So I'm graphing on the y-axis displacement, and I'm graphing on the x-axis time. And so I have bicycle A, here's my slope of positive 2. Bicycle B, that's my starting at 200 and a slope of positive 3 for A and negative 2 slope for B. Where they cross is the magical moment. And where they cross, if you did this on graph paper, which I did, you can't see the graph paper, t is at 40 seconds and s is at 120 meters right here. This is really cool. We'll do a lot more examples like this coming up.